you should be seeing the slides now, right?
Yes, we do.
Great. So the first topic is about explainable AI. So the outline of this talk is that I will first give an introduction to the topic. So in this talk, I will be going through explainable AI methods for images and deep learning. First, I will go through pixel-based explanations, so Lime and Chop, and then I proceed to the gradient-based heat maps like RedCam and so forth. Then I will also go through pre-modeling explainability, so how to look into your training data. And then at the end, I will go through a few alternative methods for explainability. First, I want to say about this terminology that I will be using in this talk. So sometimes this topic is divided into three different categories. And these categories are meant to explain, interpret, and understand AI. In this talk, I will refer all of these categories as explainable AI or XAI. Just because there is a lot of debate that what methods are actually interpreting the AI and which ones are explained and so forth. So I would use only one term to make matters simple. So about myself, I'm Sara Ta, and I have a research background. So I have a PhD from theoretical particle physics. Previously, I worked as a machine learning developer in computer vision and deep learning. And now I'm in a project, explainable AI project in my current job at Dane Studios. And we are part of this IGA consortium that is a project that is partly funded by Business Finland. And in this project, I act as an XAI researcher. So I go through papers and then suggest different explainability methods that we could try out and then also test these models. But I can't, unfortunately, reveal that what methods we are looking into or share any of our results. So let's start by a brief intro to the topic. First, I will briefly explain the deep learning because I know that not everybody here is a data scientist. So let's think about the simple case. In the simple case, we have a large image set, and in these images, we have also the class labels. So for example, there is image of a cat, and then the label says that a cat. Then we also have a complex model called neural network. And in this network, we have millions of tunable, or often millions of tunable parameters. These are organized in layers that are connected with weights. And if you kind of think that what means the training phase, you can kind of like say that you try to fit the data into a very complex model. So what happens when you use it? You have an image. You give this image to a black box, which is your model. But because the model is so complex, you don't really know how the parameters are connected with each other, or you can't understand how they are connected. There is nothing mysterious going on, but it's just so complex that humans can't understand these complex models. So then the black box just outputs a result. Sometimes the result makes sense, sometimes it doesn't. This is completely like I just made up this example, but very often, as I've used these images, very often the predictions doesn't make any sense. And there is no way to know that what actually happened. So there is this increasing demand to somehow explain that what the model did and why it predicted the output it did. But there is this problem. If you want very accurate results, you you need to use complex models. So the more complex your model is, the more accurate it is, but the more difficult it is to explain. So if you think about a simple case where you have data points and you fit a line to the points, then your output changes. It's easy to explain that now the prediction is here because it simply follows the line. But with neural networks, when you have millions of parameters that affect to the results, it's really difficult to give any kind of explanation why the outcome was what it was. So even though the explainable AI methods try to summarize what goes on in the method, it will always lack some certain details. So remember that the deep learning models are very complex, and the explainable AI is able to summarize only a small part of it. So it will never explain them fully. But sometimes that is enough that we understand a little bit more. Then these explainability methods are directly linked into data ethics, because if you can't understand what your model is doing, how do you know it's fair? There is these typical AI blunders from the previous years. So for example, Google that identified Black people as gorillas, and then Zoom with virtual backgrounds that made some people that were very Black or very white to lose their heads. Then there was this Amazon Carry service that recommends mostly males, and the reason was that majority of the workers were males. So the model learned that women are not good fit for this purpose. So if a good candidates were simply ruled out because in their CV it read like women or women's, like women's basketball team captain. And that's why it ranked only males too high in this career service. And then there was this case that, for example, healthcare algorithm in USA that failed to flag serious illnesses on Black people. The reason for that was that white people have better healthcare, so they are diagnosed more probably. So when the algorithm was asked to find serious illnesses on the patients, it preferred white patients over Black patients simply because the data was biased. But it's important to remember that it depends what kind of questions you want the explainable AI to answer. Depends a lot that what kind of role you have in this process. So for example, data scientists, so you can kind of divide this target audience of explainable AI into 5 different groups. The first group is data scientists and developers, and they want ways how to improve the model, train more efficiently, and validate the results. Then there are domain users, so for example, doctors and bankers and so forth, that are in their work using this AI. And there it's important that they trust the decisions made by AI, but they also need to understand what it's doing. Then it's also important to know the problematic cases so that they can look deeply into those cases. Then there is these regulatory entities and lawmakers that need to make sure that the models are fair and that the model works as promised. They need to also understand the idea behind the system and evaluate if that's appropriate. Then there is also managers and decision makers that need to understand the application, its limitations, and their potential value. And then there is the last group, which is users. The users, the most important thing in this group is that the users have right to know knowledge on decisions affecting them. There is this famous GDPR rule that if you actually apply it very strongly, it actually says that you shouldn't use deep learning because you can never fully explain that why the decisions were as they were. But luckily, this is not applied that strongly, at least now. But also in this group is important that you can verify that you are treated fairly. So if you get suspicious that is it perhaps some gender or racial bias that affect how you are treated, you need to know that what is the features that cause this prediction. And then you have to also be able to correct data if you notice that it's wrong. And just a word of caution, this is a very hot topic. And as in this field, technologies come and go. There is this famous Gartner hype cycle that tries to model how new trends always come and how they go. So at the beginning, there is this hype phase where the expectations are like, it's loaded with expectations, how it's gonna solve all the problems and so forth. But soon when they start applying it, they notice that they are not gonna meet the very high expectation, and then there is a drop of interest. So the explainable AI is at the top of the hype about like now. So if you read something about the explainable AI, always remember to read it with a critical eye, because there is a lot of unnecessary hype and promises that cannot be kept. So just the word of caution. So if you read that somebody is saying that we can see in the brains of AI, or we can make the black box transparent, or any kind of these words, it's very probably to be bullshit. So I will go through these most common methods first. So limit and shop. Because of this project and also because of personal interest, I've been looking a lot of webinars on explainable AI. And in those webinars, it's very common that they say that, okay, we're going to list all the explainability methods and so forth, what you can try. And I always look into them because as a XAI researcher, I want to know that what kind of methods they find. And then I'm always a bit disappointed because the methods that they discuss about is mostly line, shop, sometimes GradGam, but that's often it. But these limit and shop are very important methods. So the idea is that you have an input image. The model predicts that it belongs to a class A. You want to understand that why, which pixels contributed to the prediction. And instead of looking into the model, as this is model agnostic, it doesn't need to know about anything about the model. So instead of looking into model, it starts making changes to the input image to see what is their effect to the result. And it makes these multiple tries of this, and then it can make a conclusion that these pixels affected the most. But because it's almost impossible to go through all the possible combinations, they compute different, limit and shop work a bit differently in the background. So limit in the background trains or approximates the prediction with this thing called surrogate model. And that's why it's a lot faster than shop, because it approximates the output better and quicker, but the problem is that the surrogate models are not always very good. This means that the limit can produce clever results, or sometimes it's a bit of conflict. Do the explanations make sense or not? Shop works differently. It requires a lot more trials, so you have to compute a lot more change a lot more this input image, and then calculate the predictions. So the idea is, behind the shop is game theory. In game theory, there is this thing called player score. And the player score tells that if you have a team of players that compete against other team, the team either win or loses. And they want to know that which is the effect of each of the players to the outcome. A high player score means that if the player is playing in the team probably wins compared that the player is not playing. Whereas a low score means that if the player is playing in the team probably loses than if the player is not playing in the team. So it uses the same tactic, but with pixels. And that's why it has it's good because it has a strong background from game theory. So just to list through the good and bad points of Lime and SHAP. So first of all, these are very important because they are independent of the model. Also, they work with different inputs. So tabular data, images, text, so forth. It's also easy to use because there is many ready-made packages. But then as the bad sides are that they are very slow because they make modifications to the image and then see the result. And especially SHAP is super slow. And also if you use SHAP, remember that it underestimates the impact of correlated features because the game theory or the player score assumes that the players are independent of each other. Then also the results are not always very convincing. So Lime is not very accurate to make these explanations. And the SHAP gives more accurate results, but it's often not good at explaining beyond the highest class. So the explanation kind of reduces very quickly. Then also Lime has these stability problems that if you add small amount of Gaussian noise to your image so that you don't see it with human eye that it has been changed, but the explanation changed. That's why combining the pros and cons, it's often that SHAP is clearly preferred compared to Lime because SHAP is more stable and even though it's slow, it's still if you need to choose between these two models, I would suggest that you use SHAP. But then going into model-specific models. So here's the idea is the same, that you have an image and you want to know that which pixels affect to the output the most. But instead of starting making changes to the input image, you actually you look into the model. And there you first compute once the usual, first you compute the usual forward pass through the network to get the predictions. Then you compare or choose one of the classes that you want to understand or explain. And then you calculate backwards the explanations to see that which pixels actually affected most to the output. Because this is kind of an inverse problem, there is different ways how to sum up these weights. And there is different alternative methods how to do this. So if you have a problem, it's often good to try out different gradient-based methods to see that which one works best in your model. But this is very fast because it only requires one forward and one backward pass, and that's it. So one example of these gradient-based methods is saliency maps with vanilla gradient. So it's very simple, fast, and robust. And then it's often visualized such that there is a heat map, where hot means that there is a big impact on the model's final decision, and cold means that it has a low impact on the model's final decision. So for example, here is images of church, tractor, and manta ray, and then the explanations of these predictions. But the problem here is that it's not very class specific. So saliency maps for cat and dog are almost the same. That's why you can't really explain that why did the model see a cat in this image or a dog in this image. To solve this problem, there is breadcrumb. And the modification is really simple. So in one part of the network, you propagate back only positive gradients. So those pixels that has a positive effect to the given class. And the reason is that sometimes positive and negative gradients kind of neutralize each other. So now they only pass through the positive ones. And now there is better distinct maps between the classes. Now it's clear to see that, okay, these are the parts of the image that resulted in cats, and these are the ones that resulted in dog. And if you want a fine-grained map, you can use this guided breadcrumb to make very detailed explanation of your model. But with these gradient-based models, there is often this question that is it actually explaining the model or simply the inputs? So there is this one study that compared different gradient-based models and compared their results to a simple edge detector. Edge detector doesn't need a model or training data. It's very typical computer vision tactic, and the idea is to simply compare the neighboring pixels and see the brightness levels, and then it detects the borders of the image. And as you can see that these explainability methods, many of them actually resemble a lot like this edge detector. So they went further and started to change the learned weights into random weights. So they started to randomize the network layer by layer, and they noticed that some of these gradient explanations, even though the network was completely randomized, still managed to make reasonable explanations. But for example, breadcrumb didn't work after making these random weights. And they also tested this, that what happens if they train with completely random data? Can they still make reasonable explanations? And they figured out that yes, they can. So the problem is that it seems that many of these methods actually doesn't explain anything about the model. It explains the input, and we know the input, so we don't need to be really explaining that. So this raises the question that, are these actually any good, these kind of explanations? At least I'm not a big fan of these, because you never know that is it that your model sucks, or is it that your explanation sucks, or is it that they both suck? So going forward, so looking into the training data, this is called as the pre-model explainability. So before you train a model, you actually look into the training data and try to explain it. The training data has a big impact on the final model. And there is this saying that garbage in, garbage out. And the network very easily learns from the bias of the data. So when you start a new project, it's very common that you want to see some data. So you randomly select some data from each classes to be able to compare that, okay, these kind of images are in this class, and these kind of images in this class. But the problem with this random set is that it doesn't actually tell you that which ones are typical data points and which ones are rare cases. For these reasons, there is this idea about prototypes and criticisms. So a prototype is a set of images that sufficiently well presents the data. It can be considered as typical data points, and criticisms are those ones that are not well presented by prototypes. So kind of the outliers or rare cases. And with this approach, that if you select prototypes and criticisms from the image set, the human can build a better mental model of the whole complex data space. And how this actually works, there is two different methods. The first one is the statistical. It's called the maximum mean discrepancy. I won't go into details of this. You can read them in the paper. And then there is the second one called adversarial method. And the idea in this is that you make small modification to the original image. And this modification is not random. It's optimized by the gradient approach, where the idea is to make as much impact to the to change the predictions as possible. But if you make such multiple of such modifications, but the predicted class still stays the same, then it's considered as prototype, as kind of very strong case of this class. Whereas if it's very easy to change the predicted class, so it changes only one after one change, then it's considered as criticism. Here you can see the comparison of these two methods that are done for the class banana. And as you can see, the prototypes looks kind of like what you would think that the banana class look like. And in the criticisms, you have clearly rarer cases. But you can use this to understand the training data, but there is also other interesting applications. For example, you can analyze the mistakes that your model did. So when you notice that this set of images were wrongly labeled, you can use this prototype and criticism method to see that what kind of things are typical mistakes and what are rare mistakes. And then by looking into that, you can perhaps detect some patterns in the errors. One important thing also was that with this approach, you can actually find biases. In this paper, they looked at the prototypes and criticism of the basketball class. And they noticed that in the criticism images, 90% of the images had at least one white player, whereas in the prototype images, 78% of the images had one black player or more. So it led them to think that the data is biased. And to prove, so because of the training data is biased, the model probably will be too. To prove this hypothesis, they went and downloaded similar image pairs from the internet. And as you can see, these two rows show very similar images, but the network seems to be looking at the faces of the players to detect that what is the sport that they are playing. And black people are clearly playing basketball. But with the white people, there is more difference in the classes. The funny thing is these ping pong players, because I am not a sports person, so previously, before doing this research, I didn't know that there is this stereotype towards Chinese ping pong players, but that's actually a bias that more than one explainability method can find from the training sets. So this is to find these prototypes and criticisms is very nice way to show that what are the typical and rare cases of an image set. But there is I would see at least a lot of different applications where you could use this. Then going forward, this is now one of the alternative methods. So this is not very widely or very well known. This is a method called testing with concept activation vectors. And the idea is to find biases in the model. For example, you could ask a question that is a concept called gender and important for a doctor score. And for this, you need images of doctors, then you need to have a trained model, and then you will have the final score. And the idea is that you compute this TCAF score, and based on this score, you can say that yes, the gender is important for the doctor's score or no. And how this works, in the paper, they give this example that are stripes an important concept in the class zebra. The setup is that first you need to have the concept images, for example, stripes. You can use, for example, Google search to find those. The more you have of these stripe images, the better, but they said that this might work already if you have 30 images. Then you need also a random set of images that are not used in the training and doesn't contain the zebra class. And then you need the images of zebra. Then the actual method is a bit more complicated, and I don't explain it very fully. But the idea is to select one layer from the model. Then you compute the stripe images until that layer, and also the random images until that layer. Then you try to train a linear classifier that identifies the striped images and then the random images. Then you take the zebra images. First, until the layer that you are looking at, you compute the zebra images as normal. Then in this layer, you actually push the zebra images towards to be a bit like more stripy. So you use this linear classifier to make the images to look a bit more stripy. And then you carry on calculating the remaining part of the network. Then you calculate that if the zebra class got higher values because it was made more stripy, so more than 50% of the images got a higher zebra class due to this modification, then it means that the stripes is an important concept in the zebra class. And so the results, they were able to find some common sense biases, like red is an important concept for fire engines, stripes for zebras, and Siberian Husky for dog sleds. Then they also find some gender and race biases, like these ping pong players that I hadn't heard about before looking into these methods, but apparently it's a real thing. And then they find also that there is a high correlation, or the female gender is very important concept for the apron class, which kind of makes sense. And so, and also is a baby. So as a conclusion, I would say that this is a promising idea, but the results are not very ambitious. And I would say that more tests are needed to see that if it's actually a viable method or not. And then going to the last method, so counterfactual visual explanations. I would call these a bit like poor man's what if tool for images. These what if tools are very important for, or were very much wanted in tabular data. So for example, if you are applying for a loan and it gets rejected, you want to know that why, like which parts should change so that you are accepted to have a loan. And then you can get results like you need to have more savings or you have to earn more. But that's easy with the tabular data because you can use statistics to calculate that. But with images, it's more difficult. And that's why this method, I wouldn't take it too seriously, but I just want to say that there kind of exists a what if tool for images. The idea is that you have an image and then you want to change the prediction of that image. For example, you would want this image of 3 to change into 5. Then you start making changes according to this tree structure image of 5, and start making edits to make the number 3 to look like 5. And as you can see, I would say that these results are a bit like bad copy of the structure image, and at least I wouldn't see very much the benefit of this. But then they use this also for the birds. And the idea to use the bird species is that humans are bad detecting different bird species. So could it be that AI will help them to teach that? And in this bird dataset, the dataset contains information on how the bird is oriented. That's why you can find very similar to structure image from the image set, and then make very reasonable results. For example, in the first case, changing the head will change the prediction. And on the second example, if you put the yellow dot in, it will change the prediction. But if you don't use the orientation and you choose the destructure image randomly, then the results doesn't make any sense. So you get these monster images, and I don't think that this will teach anyone about the different bird species. So I wouldn't take this too seriously, but if there is some reason you need to have this what if tool for images, this is one that you could use. Okay, so that was all that I managed to fit into this 25-minute presentation. So as a final remarks, remember that AI models inherit and magnify the bias of the data very easily. And that's why it's also important that both the training data and your model. Explainable AI is very important, but it's badly hyped topic. And remember that explainable AI is always approximation of the full solution, and it always lacks some details. Also, don't trust blindly on one method. Try to use different methods instead. But then there is the very important thing that if you use XAI correctly, it helps us to make better and more fair models. And when I was going through these papers, I found one blog post that listed some XAI software packages that contain some of the methods that I showed in here. So if you want to take a look, there is the link to it. But many of these methods are still not very mainstream, so you can't find them in the packages. You have to do a lot of coding yourself in order to test them. So thank you from me and my home colleagues. And if you have some questions, please contact me via email or via LinkedIn. Thank you.
Thank you, Sara. That was really interesting and really insightful. So I have a few questions from the chat. Again, if you have any question, you may ask them. You may write them down in the chat section. For you, Sara, I have two questions. Okay. First, a question from Htinen, which is, can some of the methods you described be used to counter some attacks on neural networks? For example, pixel alteration.
So what kind of attacks? Can you repeat?
You may also see it in the chat section. Okay. Well, I'll repeat it. Can some of the methods you described be used to counter some attacks on neural networks? for example, pixel alteration. I think, if you, in some cases, I guess, about this question, in some cases, you may alter the image, for example, you may add some noise or something that may cause the model to make a different prediction.
There is methods that can do that. So you can make attacks to the network by calculating the most effective way to inject the network and change its prediction. But if you think it's vice versa, it's a lot more difficult to find these kind of attacks. So I haven't found that kind of explainable AI methods that could find that now these images are tried to be attacked with some method.
Okay. So another question, again from Honain. Do you think that more explainable AI methods should be used to fix models and remove their biases, or rather inform us about our own biases?
Well, I guess it's a longer question, but yeah. So I think the idea is to try to fix the models and remove the biases. But to inform us about our own biases, it's a bit more difficult because the majority of the training data is collected from white, rich countries. So that's why the data sets are often already biased. And then there is a lot of problems that, for example, if you collected the data kind of like wrongly, so many collect them, like, for example, using news articles. There, for example, Black people as criminals are sampled very high, and often Black people are not presented as in a good light. So that's why how you collect the data is actually more important than what kind of biases the people might have, I would say.
Okay. Yeah. Thanks.